E2 elimination from six-membered rings. So as I said, six-membered rings are going to be slightly different because they have a restricted amount of rotation. One rule that we need to follow with a six-membered ring is that in elimination, the hydrogen and the halogen must be in axial positions for the anti-elimination to occur. So what this means is that is going to affect rate of reaction. So if they're not in the axial positions, remember we can do a ring flip, and ring flip will give us equatorial position switching to axial positions. What the most significant thing about H and X having to be in axial positions is that their location on the ring is going to affect the rate of reaction. So let's explain. Both H and Cl, for example, must be axial in order for the reaction to occur. For the ring shown, I've drawn in the two hydrogens at the adjacent carbon where a proton would be abstracted to lose the chlorine. In the more stable conformer, chlorine is the largest group and it is in equatorial position. Because in order to be eliminated, chlorine needs to be axial, a ring flip has to occur, but this is the less stable conformer, which means that it is present in solution for a lower amount of time than the more stable conformer is present. Which means that in order for the chlorine to be eliminated, the more stable conformer has to undergo a ring flip, and that takes more time. So reactions where the chlorine and the hydrogen are in the axial position only in the less stable conformer are going to be longer in time and have a slower rate than reactions where they are axial, hydrogen and chlorine eliminated are axial in the more stable conformer. Okay, so this elimination is going to eliminate chlorine through the less stable conformer, and we get our alkene. But because chlorine and hydrogen were not axial in the more stable conformer, the reaction takes longer. Wow, not what I'm trying to do. Okay. What this means is just a pen, slower reaction or slower rate when we use the less stable conformer. Remembering that the rate constant for elimination depends on the equilibrium, and the value of KEQ depends on whether the more stable conformer or the less stable conformer is where the hydrogen and the chlorine are axial. So for the reaction that takes place through the more stable conformer, with the product being the more stable conformer, then the rate will be very fast and KEQ will be large. For the reaction that takes place through the less stable conformer, as the product, then the equilibrium will be small and the rate of reaction will be slow. All right, so let's look at when the reaction will be fast. So elimination occurs through the more stable conformer, then the reaction is fast. So the more stable conformer has the largest groups equatorial. So you can see both methyl and this isopropyl group, CH-CH32, which in skeletal structure looks like this. This is the more stable conformer because these large carbon groups are equatorial. Now, with this being the more stable conformer, we note that the hydrogen that is eliminated and the chloride that is eliminated are anti and axial. So we can perform an elimination directly from the more stable conformer, losing chlorine, or this is E2. So we remove the hydrogen, the electrons collapse, and chlorine gets kicked off. So we have a base. In this case, the base is ethoxide. And base comes and takes the hydrogen. The sigma electrons of hydrogen form a pi bond, and the chlorine gets kicked off. And that gives us our alkene. And the reaction where for the less stable conformer with the two largest groups axial, the CH3 and the CH-CH32, the hydrogen and the chlorine in that case are equatorial, and so no reaction through that conformer. Now, when will the reaction be slow? The reaction is slow if elimination occurs through the less stable conformer. So here our example is that the more stable conformer has, again, our large methyl and isopropyl groups in the equatorial position. But note that the chloride is also equatorial. And so a reaction cannot occur with this conformer. No reaction from this conformer, because chloride must be axial. And so what has to happen before a reaction can occur is a ring flip. And so you can think of a ring flip as taking more time. Time consuming. And then only after the ring flip occurs is the chlorine that we need to remove axial and the hydrogen axial. But then these methyl groups and isopropyl groups are also axial, so that is why it's the less stable conformer. So once we have removed this hydrogen with our base, then we get our alkene, and this reaction is slow because of the going through the less stable conformer. For E1 elimination, it does not matter if the chlorine and hydrogen are axial because it goes through a carbocation. So remember, for E1, the carbocation, we don't have to be anti. E1, the H and Cl do not have to be in axial positions. And that's because it's not a concerted reaction. So we can show for an E1 that this chlorine just falls off randomly. We form the carbocation, and only then does the base come in and abstract a proton. And then the pi electrons, or the sigma electrons, move into the pi bond, and we get our double bond. Okay. The next topic that we'll cover is SN2 and E2 reactions of alkyl halides. So, will we get SN2 and E2 reactions at the same time? It depends on the substrate and the amount of substitution and we might get both, but we may not get them made in equal amounts. All right, so a nucleophile can attack a carbon and kick off a bromine to make a new bond. But a base removes a proton to make a new pi bond and remove a halogen. Notice that in both cases, hydroxide is used as the nucleophile and hydroxide is used as the base, so that a substitution product and an elimination product are produced from the same starting material and the same base/nucleophile. So why wouldn't they both be formed at the same time? And the reason is what we already covered. In an SN2 reaction, a primary alkyl halide reacts more quickly than a secondary or a tertiary. But in an E2 elimination, tertiary reacts more quickly, and then a secondary, and then a primary is the least likely. So if we have this primary alkyl halide, then the major product is going to be the substitution product, because primary carbons favor substitution and primary carbons are the least likely to favor elimination. So the substitution product in this case would be the major product. And if any elimination product forms, only a small amount. So it will be minor if it forms. Under SN2 and E2 conditions, we will have a strong base. For primary alkyl halides, they primarily favor substitution. So we show a primary alkyl halide, 1-bromopropane plus a strong base, formally charged methoxide ion. Methoxide ion is favoring substitution at 90% and a small amount of elimination at 10%. So substitution is favored, but the elimination product is still there. So we have a regioselective reaction where the major product is formed through substitution, but we do get a minor product in elimination. Now the note that I have on the slide, that a good leaving group is the conjugate base of a strong acid, is because not all leaving groups will be halogens. We're going to study later that any leaving group, which is the conjugate base of a strong acid, will be a good leaving group. So for example, one of the leaving groups used frequently on the ACS exam is abbreviated as OTS, which is toluene, paratoluene sulfonate ion. So this is the conjugate base of the strong acid, paratoluene sulfonic acid. And any acid which contains the sulfonate group, SO3, is going to be a strong acid. So what this would look like bonded on a molecule would be that we would have, instead of bromine, the sulfonate group bonded. So this molecule could replace, instead of the alkyl halide, we could use this, but we would get the exact same product. So that would give the same product. So while this chapter focuses on leaving groups being halogens, don't get stuck thinking that halogens will be the only leaving groups we ever have, because that is not true.